Hello and welcome back to my show. Today we're going to be doing a bit of work in Leaf, and what we'll be doing is working with a linked list. And by linked list I mean we'll be building a linked list, a simple linked list in Leaf, and I'll show you basically how it works and go over some of the complexity of it and the theory behind it and how the language works. And this will be forming part of a new series on collections and algorithms and other such fun computing things. Well, without too much delay, let's just get started. Close this off here. This off. And we'll just start with an empty slate here. And Leaf is my programming language. I'll be using this. It should be easy enough to follow along. I will just talk about some of the syntax and what I'm doing as I do it. And if you have any questions, just feel free to ask. If you don't catch the show live, just send them to me on Twitter or off of my page. You can send comments in the articles or in the Google groups, and you can see the links from my page at mort-ora-y.com. And a linked list, we're basically going to start with a class, and so a class is going to be a linked list. And a linked list is a parametric class. What this means is that it takes a type T. Let me zoom in a bit. Instead of any old type, we're going to take type T. That allows it means anything can be stored in this list. And let me just go and save this file. Okay. Where is that? We're just going to leave algorithms. Linked list there. I tested a few things before just to make sure where it works, but now I'll do another one called main.leaf. And we're going to import a module standard as well. This looks the normal language so far, and let's declare the main so we have something here. This little arrow with nothing on it makes all the arguments implicit, no arguments, and it has one return value. This would be equivalent to writing this. It's just a bit clearer to write this. And we'll just show this is working first with hello, just so we get the basic syntax. And then we can run this here. Leaf, or main.leaf. Okay, it says hello. There's no actual automatic line feed. If we do print line, show that again. Let's just clear the screen. Requires tuple, yeah, of course. Okay, so it prints hello, and I'm just showing the basic setup of Leaf here right now. And we're printing a line called hello. And now we'll start with the linked list. And the linked lists are a collection of items where one item points to the next item. So we're going to need a node in here. What that means is node is that each item is going to have a value, and we have to have both the value and what the next value is. So you're going to put a class node here. And it's going to have a value, which is a variable value, and this is what's actually of type T now, is this value. It's saying whatever we have in it. So let's create one in main, var L, I just call it Q, I like Q because it's easier to see. This is a linked list of T. Now I notice at this font size we can't see the underscores, so I'm going to go one smaller so we can see underscores. This is a fault in Kate. It kind of bothers me that you sometimes clip off the bottom letters. But now we have linked list T, but it can't be T, it has to be something specific. So let's say it stores integers. And now we have no T, so this means as a linked list of integer, we'll have the linked list, and all T's here will be integer here, and the node will be integer. And what a node has is it has a next node. Next is a reserved word though, so let's just say, let's just call it next node. It's a bit redundant, but this is sometimes complicated when you have simple words and they clash with language words. You have to give them some name. And the next node is also a node, but we have an error here. And the thing is that node, everything in Leaf by default is what's called by value. These are not by reference, and this is in contrast to many other languages where things are by reference by default classes. This is more like C++, where all of the things by default are by value. So you can't have a node that contains a node by value, because this would be of infinite size, because the node contains a node. But if you have something of, but you can have an optional node and may not have it, which is the first thing we want, but this is still by value. So what we want is optional shared. Now this may seem like a little bit redundant, but this makes it very clear in the language exactly what you get here. Because by default, if we just put shared, this is another way, this would be closer to what, say, C# would do by default for objects, that all objects are shared. But in C# you end up writing non-nullable on things that you don't want nullable, and so Leaf is taking the other viewpoint, is that everything has a value by default. If you want it optional, you have to explicitly say it's optional. So we're going to mark this one as optional. So now we have a node which has a value and a next node, and our class linked list itself, it needs to have a head. This is the first node in the list, and it's also an optional shared node. And this is the first one on the list because we may not have anything yet. And the main function we want to do is append. We want to add something to the node. And what we're going to append is a value of t. We don't know what that value is. And we'll do the first one here is, we have to check when you add something and it's in the list, do we have a head or not? So we have not has head. Head has a check that says, does this value have something in it? Is there actually a value in head? And not is of course not. And this is how you do the if-then construct. If we don't have head, then we have to create a new node for head. Then we say head equals node t. This will create the new node. And it has to be shared. This is where it gets a little bit interesting. We have to create a shared node. So now we're going to say type shared node of type t. These little brackets here, these are the parametric type brackets. I've opted for a node not to overload any other types because this, or any other symbols, because this creates a parsing problem and syntax problem when you have too many things meaning different things. So we did it this way. And now you can just say head.value equals x, and that sets the head value to x. We won't worry about the else for now, and let's add at least one thing to our list. And let's add the value 7. Okay. Now, we should be able to write out this value 7. Well, let's just say this so we actually get it there first. Probably get an error. Unfortunately in Leaf yet, I don't actually have the proper error messages, so we're dealing with like very low level sort of error messages at the moment. You just kind of have to know from the location, so towards 15, 17, what the problem is. Okay, and this is because head is optional. We have to dereference this. So what we may want to do is actually create the value first, create a new one. And this is a very standard approach to assign it all at once, head that value equals x, and then assign it to head. And the reason is because head is optional. You can't directly modify head. You can't directly access it. So now we have nothing. Let's see if it's actually there. So what we want to do is we want to print something from head. Print line. We want to do q.head.value. But there is no actual, because this is optional, we have to get at the optional value. This is just the long way. This is how optionals work in Leaf, is that we say get op, but this is actually, this code is somewhat error prone because if there is no q head, this will raise an error condition. So the more correct way in Leaf to do this is to make an optional thing, and you use like or equals or value. With this setup, it's a bit weird, but we should be able to say, because it's question.value, and this will be optional, and then say or 5. Okay, now let me explain what that syntax means first. The question dot, this bit right here, question dot means if head doesn't have a value, then the result of this is also optional. That is, all of this means optional. And the OR then means, well, if we don't have that, then write out 5 instead. So if we didn't append this value, it writes out 5 because it doesn't have a head. So the result of Q head.value is not set, and then it becomes an optional value, an unset value, and we write out the value of 5 instead. And when we append it, then we see we have a value and we get 7. These are just some of the syntax we work with. And now if you want to append another value, it's going to do nothing. Let's say 8. Nothing happens because we can't write it out. And so we might want to write out the next value, where this is getting really questionable, q.head. And then we want the next node. And this may also be optional, so value, or let's write out 0 this time. Put these both at 0 because we're not expecting them. Okay, I have the wrong type. I'm not sure what's actually wrong there now. This is actually a lower level compiler error, so I actually made a mistake here somehow. In the Leaf compiler, probably. Okay, but accessing deep down isn't an issue anyways. We should probably make a proper iteration function now instead. So let's just ignore that error. I'm going to make a to-do on here later. To-do should have worked, even if ugly. And this is for me to fix. Let's write a function out that dumps what's in the list. Let's say dump Q. We know there's only one on the list now, but I just want to show the dumping function before we get further. Dump equals Q linked list. We can make the Q take a linked list of any type either. This is where we say any in this case. And I'll get back to why we say any and not T here. And so we say the head is equal to Q.head. Now we can, let's say the node. And now we can say while has n, we're going to loop the standard.println, one per line, n.value, n equals n.next node. And okay, and here we're going to do get op because we know we have n. Now it's safe because we said it has n, but we still have to actually get at the value. 37 dump Q. Okay, it's incomplete because I typed linked test and not linked list. Okay, 7. Why does it print it twice? That's, oh yeah, because I printed it here still. So let's get rid of that. Well, we should have 7, 8, and that's because up here we don't have a second value. Now this is where the first problem of a linked list comes in. If we only link to the next node, to add to the end, we're going to have to shuffle all the way off to the end to figure out where that end is. So we're going to have to, because if we have a second node, we don't know if we have a third node. So let's do it the long way first. Let's write the code that loops through and gets to the end. So when we get to the end, we're going to start at the head. And now we're going to say while has e.nextNode. And we know head exists at this point, so we're going to get opt. Well, we can actually do this, question dot. This should loop forever at this point. And this is going to be the same error, so I must have made a mistake here. This is the same error as down here. So I have something wrong with an optional when I do question dot on optional. So let's just make it simple. We'll just get at the opt. Well, it has e.nextNode, and we simply say e equals e.nextNode, and we get at the optional value. This is saying, okay, it's not optional, we actually have it, and this will get us the end. And then we do what we did like before. We make a new node, shared node of type T, h dot value equals x, and then e dot next node equals h. Now we print 7, 8. Let me add one more value so we're convinced this is actually working, because the first one is okay. 7, 8, 9. Okay, 7, 8, 9. We have the 3 values written out in this basic linked list. And let me explain again how this works. So when we go to append, so we call append 3 times. When we go to append, we first check, do we have a head node or not? Because we need to start somewhere. And if we have nothing in the list, then we don't have a head node. Then we create a new node, and we add it to the head instead. If we already have a head node, we have to find the end. Find tail node, as we call it. Tail node is the one that's last in the list, and this is important for later when we replace this. And that means we get at the head node, and then as long as we have a next node, well, has next node, we get the next node. And this means, and we stop before we go beyond it, obviously, so we stop at the last node. That means the has next node part. The moment we don't have a next node, we're done. And then we just add the node as normal. And we already see a bit of code repetition here. So it makes sense if we extract this out, because we're always going to create this new node and calling it h, and that's good, so end of value. So here we create the new node, and then when we have h, we just assign n, and down here we can also just assign to n. And that reduces some of the redundancy. And now we have the same list, 7, 8, 9. This finding tail node isn't so good though. It's one of the problems with the linked list if we have it what's called singly linked. When we have just this forward thing, it's actually not a problem with single list, it's a way I store things. We have no way of knowing what the tail node is, so append becomes what's called an expensive operation. Because every node we append, we have to iterate through the whole list. Append becomes a theta of 1, and this means that it's more costly. This can be a constant time instead. By theta of 1, I mean we have to loop through n times. So if there's n items in the list, this while loop does n iterations until it gets to the end. This is kind of wasteful if we know we could probably do it in constant time instead, where it's constant time, one operation. So let's make that change, and actually let's get the symbol to type theta. This is one of the problems in the keyboard. One of them I'll tell you right away. Theta is already selected, interesting. So I must use it a lot. Theta. So this is certainly something called theta of n. You'll often see in a lot of places people say big O of n. Now technically this is also big O, but big O is actually an upper limit. So I could actually say this is big O of n squared and still be correct, but it's not very helpful. And this is, theta actually says it is actually this number of steps. It's not less than that, it's not more than that, it is actually n steps. So I'm going to try and be correct here. We all have Unicode and stuff. Unfortunately, we don't have it on our keyboards, we have to use visual selectors to get at this character. And actually, there is a dead Greek selector on Linux, on Ubuntu, which I tried to get setting up and I couldn't actually get it working. I have an open question. If anybody knows how to get the Greek keyboard hotkeys or dead keys working, please let me know. I'd like to get them working because I often work with these symbols and I like to use them more often. Okay, so this is theta of n now. It's going to take n steps, and we want to reduce that to theta of 1, so it takes 1 step. And by 1 step, I don't mean the number of statements. By 1 step is like when we have a loop, we take one operation, how many times, this, and then we just want to get rid of the loop. The way we're going to do that is by adding a tail node. Optional shared node. Now you notice we're typing the same thing a lot, this optional shared node, and I'll show you just in a sec how we can reduce this, or at least within this class, because it's used quite often. But now I added tail. What tail is going to be, and this points to first item in the list. points to last item in the list. Get rid of this, so this was n. Okay, well, let's leave that for now until change it. If we don't have a head, it also means we don't have a tail. So we just assign it the tail as well. Now the first node, the node that we created is both the head and the tail. And now we don't need to find the tail node. This is why I said find tail node. We have the tail node. So now we can simply say tail.nextNode equals n, because this is where we're going. That's we found the tail node. Plus, we have to reassign the tail, because it becomes also the tail. So this is maybe a bit confusing, as tail is our current tail node, and the current next node of the current one becomes n, and then the tail node becomes n. If you put this in the other order, obviously that wouldn't work. You'd create a loop on yourself. And okay, I made a mistake somewhere. Line 25. Tail.nextNode. Yes, because it's optional again. Remember, we have to do this anytime it's optional. You want to get the value. In other than algorithm collections and algorithms programming, you won't see getOp that often, because you usually use, as I said, the question dot operator or the or operator, and or defaults are a bit easier to work with. Right. Now, as we can see, we print out 789. We have it working basically, and there is no loop here. So all we have is we've reduced it from theta of n to theta of 1. And this means it's constant time. 1 means constant time. Doesn't matter how many items I have in this linked list, it takes the same amount of time to add it. This is, of course, ignoring the cost of allocation. We don't know how long allocation is going to cost. Usually it's not technically constant time in most systems, but it's usually fast enough it's not a concern. And it's definitely not n. But we've reused at least our code, so at least our code is faster. Our code is constant time for n. Okay, and let's just add another one so we can convince ourselves it's still working. It's always good to just add a few more. The reason I sometimes do this is because what if we didn't make a change? What if it just somehow ran the old program, right? And I've actually had this happen before. You keep making changes to a file and you keep running it and nothing's changing, or you think it's still working but you're actually using the old code. So it's somehow helpful to keep changing the output to show that, look, something is actually changing. Now, let's write a sum function as well. So this was the dump of the queue, this was the dump. Now let's write out the sum of this. Get rid of the to-do. And let's write a function that gets the sum. I'm going to start with the code from dump. And this explicitly, by copying, pasting, and showing, this is redundant. We shouldn't have to do this. Why are we copying code? If it's going to be the exact same structure, we don't really want to do that. So let's start at 0, a count of 0. And instead of print line, we're going to add to it. And at the very end, we're going to do dump. Standard print line. Sum, not plus. Okay, my language is mixed up. Let's see if that works. Nope, I made a mistake on line 57. What did I make a mistake on? Not clear where I made my mistake. Sum should work. Sum Q. Well, that's a bit weird. No. Again, it's the error message screwing up. I forgot to return the value here. So what happens in Leaf is when you have points to and you don't specify the return value, it looks to the code and says, well, what is it actually returning? And since I'm not returning anything, this function actually ends up looking like this. Returns nothing. So if I attempt to use it down here, it gets confused because sum doesn't evaluate to anything. And again, I really have to work on these error messages. I've been putting it off a long time to get clearing error messages, but I'm not going to change it right at this moment, so let's keep going. And we just want to return n. Okay, and now where it requires tuple. Which line was I on? Now I don't know why it's saying that. This requires a tuple, which makes sense. What error am I making? Now I made the mistake again. If you look at here, I'm returning n, which is not, we want to return c, which is the count. Okay, now a sum of 30. This sounds correct now. And is that actually quickly correct? 13, 21, 30, yeah. Now another option here, which is actually make this clearer. And implicit typing is very helpful when you want to quickly type something, but it can quickly lead to small mistakes. If I return n instead of c, I return the wrong type, which is what I did. The compiler can't at this point figure out in this function that I've done something wrong. But I could instead just directly declare the return value, c, as an integer. And it's going to get its default value, which is 0, so we can simply remove that c, and we don't have to return it now. Its name return value is going to return that, and that'll return the same value, 30. Again, let's modify this to ensure that it actually ran the new code, so 29, that's what we want. And 30. What I mean here is that in this syntax now, c is default declared, and it'll have a default value of 0, and we just add to it in here. What we have now is a bit of redundancy between these functions. Dump and sum, they do about the same thing. They both loop over the code. What we prefer is to have code on the linked list itself which does the looping, and all we have to do is write the specific code. Now this becomes a little bit messy, but we're going to do that anyway. So we're going to write our for each function. And we'll often find this in a lot of code. A lot of libraries have for each. It's like, I want to iterate over the collection, do something for each node in the list. And this is going to take a function. And what this function is, and so I mean this takes a function itself, like we take a callback that we're going to call on each item in the list. And I'll get back to that syntax in just a second. Let's write the loop first. N equals q.head. We start at head. Well, we have n. And this is the fundamental loop. Get opt n.next node. And then we want to call function with the node each time. So what this means is function, this fn, this has to be a function that takes a node. So we're going to type this takes a node. This takes a shared node of type t. And it doesn't have any return values. And we're actually going to pass a function to this, so we take a function, and maybe it's a bit clearer when we actually see it. So what happens with dump now is dump now becomes for each, and we're going to give it a function that takes a node and prints out the value. We don't need get-opt anymore because we've already done get-opt inside the loop. And so now dump calls our new for each function. Parse or stuck parsing nothing. Okay, so I made a mistake. Sum. I've missed the ending braces. Q. Q is up here. Alright, we're inside the type now, so I don't need Q. Head is just defined here. Now we have the same result. It's what we want. We made a for each function. For each simply iterates over the items in our list, which means callers of for each don't have to have any clue how the list is stored internally. They don't access head, they don't access tail, they don't access next node, and this is what you really want. And dump just simply goes over it and prints out each item, which means we can do the same for the sum. q.forEach and n c plus equals n.value. Alright, and this is one of those weird errors. this is a bit tough to explain, but see, because we're inside a new function, and look at when we call this for each in dump and also in sum, this part here is another function. This is a lambda function, and it's also a closure. In this case, it's not a closure in anything, and I recently wrote an article on my website in closure if you want to go look at that up and see what it is. But this one's a bit clearer, is that where does this value c come from? Well, it's not part of this function. It's from the wrapping function. And there's just one restriction in Leaf, that you cannot use a return value in a closure. And I'm still debating whether this will actually be possible. So let's just put var c equals here again. And just leave that out and return c. We can capture a local variable. That would be useless otherwise, so we capture that, and now we can do that. And we have a sum of 30. Now, for such a trivial amount of code, it doesn't seem like a big boon, but what we've done is we've taken out this logic for looping over the list to be generic. It's just inside linked list. We say nothing about, we don't have to keep repeating this for loop. We have a for loop, and anytime we need to go for each, we just simply call for each with this function, and we do a local capture of whatever we need. We do the output on that node, and then we return it. So now dump and sum look very much the same. For each is also, I'm going to take the data again. For each is an n, takes n, and this is what you expect for a for each. It's taking n steps to go through each item in the list, and you may be asking yourself, well, that's silly. Why would it be any number any other than n? Well, obviously it can't be less than n. There is, the lower bound is n, because we have to at least visit each item in the list once. But it's quite possible for some data structures to have a higher number. That is, it might take more effort on a data structure to actually iterate over the items. Some of them are not constructed for iteration. A linked list is meant for iteration. It goes really quickly. So a linked list for us is just n. We know that, but this is it. There are some data structures which take more than n for iteration. We'll eventually get to them in this series. They start getting more complex. Most of the data structures, the simple ones, all have theta of n for the iteration. Now, let's make something else interesting. First of all, let's change for each to not actually print a line in each one. We'll just print each item out with a space, because as our list gets bigger, we don't want it so long. So it's a 6, 7, 8, 9. Increase the font size here too. Okay, 6, 7, 8, 9. I talk about another small peculiarity in Leaf. Is you notice the print function takes a tuple. I have to put the brackets in. This is because the language, well, it supports variable arguments for the purpose of interacting with the C API, like old APIs, because it has to work with them. And I'm debating whether to allow it on high-level APIs as well. So right now, these print functions, they take a tuple instead of just a variable list, instead of just saying this. It's not the highest thing on my priority to solve that. And other than print, there's not so many functions where you really use this, but they do come up often enough, and we're going to find out how often they do, like for debug functions, logging functions, that it might be worthwhile for us to actually add an implicit way to do these tuples. But for now, let's leave it like this. I just wanted to explain that. Now, what if we wanted to reverse this? What if we want to start at the tail of the list and print out backwards? This is with our current list, this can be done. So we want to do a reverse dump. Let's just say reverse dump. Start with dump. And it's going to be exactly the same, except we want to do a reversed for each. For each, and probably call it for each reverse. Print them all backwards. Now we have to see what it takes. How do we print this stuff out backwards? For each reverse. Well, we know it's going to take the same function here, because that's what we want to print out. It has the same type of contract as the for each. It means same signature. For each one, we're going to print it out. But we have to start at the tail node and go backwards. We can't simply start at the tail node. The reason is because we have nothing pointing back to the previous one. And this is what we'll get to next, how we fix that. But how do we do it without? If we have a forward singly linked list, how do you do a reverse iteration? And we're going to actually use recursion for this now. We're going to define an internal one, define for each reverse. I'll just call it impl, and it's going to take this function and it's going to take a node where it is. Put this on the next line. It's going to take n, which is shared node, okay, shared node, that's the node we're on. And now we're going to do this. Since we have a node, it's shared, we're going to say, actually let's say it's optional, just to capture a bit more. If we don't have n, then return. We're done. There's nothing here to do. We're done. Otherwise we have n, then we're going to say if we have n.nextNode, then we do for each reverse impl past the function and get the next node. What is that? So these are two steps. Not n means, well, we don't have a node, so we stop. Now we say if we have a next node, let's do that first, because we need to start from the final node. So we do that. And now we have the current node, and we call the function on the current node get opt n. And we have to start this off for each the interconnection function with the head node. And that should reverse it. We need to actually reverse it, so let's do dump reverse. Forgot to call it a different name. Okay, and I have an error somewhere, 48. Alright, because we don't have n, has get opt n. Okay, now I made a mistake somewhere. This is sometimes a little bit tricky when we have the inferred typing, that there is a small phase in the compiler where it might be getting stuck on something. And now we do that. And see, it didn't set out a line number, so it's a little bit tricky now. I had to figure out what that line number is. And it's probably because of this right here, is we implied the return values, and we're calling a function with implied return values. And the easiest way to fix some of these is sometimes just say, look, there's just no return values. It's not implied, they just are none. Okay, and now we get a different error, which is good, on line 49. For each reverse get opt n next node. See, no, we don't call next node. This way, we don't actually have to do next. We don't have to check as, because we're doing this check for has directly in the for each. This is the reason I did it. I just wanted to do this. Directly call it n.nextNode. We do get opt on n.nextNode. Then we simplify this. And an error somewhere. 47. Too many closing braces or parentheses. Okay. Now it actually worked. I'm going to go through and explain that again a little bit. So it's 6789 9876. What we did for reverse is this will be the public function for each reverse, and this is the implement list will be internal. At the moment, Leaf doesn't have a way to mark things as public and private. That's still a work in progress, so I just call it impl. We might want to, in the meantime, just use the convention from Python or other languages. Let's put an underscore on it and say, look, this is internal. And for head and stuff, we'll leave for now for clarity. And so for each reverse, we start at the head node. Because we have to work our way backwards, we're going to walk forward. We're going to walk forward until we get the end of the node. For each node, we're going to say if we don't have a node, putting this not here, what this does is it simplifies the coding. As you saw, I had the if statement before and realized I didn't need that. So now I can simply say if we don't have end, then we're done. We've reached the end. Otherwise, keep going on the next node. And we do this before we do anything because we want reversed. And then when we return, call the user supplied function. And this will call this on all the nodes in reverse. Now this looks like a lot of setup to do something in reverse, right? Where you have to go to the end and come back. And well, this is where the part gets interesting with complexity. This is also theta of n. This also only takes n steps, which may seem a little bit weird. Why, if it's such complexity, does it still take only n steps? And it's because we're still only visiting each item once. We're doing a recursive call, but we're still only touching each item once. There's no loop here. But this is something we have to know about complexities. These thetas, this theta n, this theta n, and the one up here for theta 1 for append, these are time complexity. Okay, so this is time. There's also something called space complexity. How much memory do these algorithms take up? For append, it's a little bit weird to say space complexity for append, but it's also the same. It just has one, and because we're allocating one new node and we don't have any loops, none of this stuff allocates anything related to n. There's no allocation related to the size of the list, so it's space complexity is 1, but usually for a linked list, you may not talk about the space complexity of append. You have to be careful is that quite often you talk about the space complexity of the entire linked list, and the entire list length is O of n. What that means is that for every item in the list, the space of the linked list in total is comparable to that for every item, and that makes sense. For every item, we have one node which links to the next node. For a collection, and this is interesting, for a collection, you typically have space of n. Anything more than this, and it starts getting hard to store data in it. But there are collections that have space of less than n. And this was one we can look at. We'll take it later in this series because it's a bit hard. It's something called a radix trie. You can actually have, this is like a compressed structure. You can have less space in it than the number of items. It may turn out that the big O is still actually technically n, but it actually has less space, and we'll have to work through the calculation at a later time. But generally, collections are going to be theta n because, look, for every item in the structure, you're going to have one bit of memory allocated for it. Anything more than that would be inefficient, but it happens. But let's get back to these for each. This first for each, this one doesn't take up any memory. It's constant. We're not doing anything. We're not doing anything at all. We're looping, which is fine, but this loop doesn't allocate any memory, doesn't consume anything. This for each reverse, this is the reason why it's important to look at spaces. This for each reverse is where we see that there's a difference. This is now space complexity of n. Now let me explain that a little bit closer, a little bit more. And this has to do with this recursion call here. When we have a function, for each reverse impl, it has parameters like fn and n. It doesn't have any local variables, but internally when the compiler compiles it, you assume there's some local variables. And these variables, fn and n, let's worry about them. they survive the entire lifetime of this function. They have to survive on this line, and this line. So there's memory allocated for them. It's a special type of allocation on the stack, but nonetheless there's memory allocated to them. So when we call for each reverse again, it means we keep the current values of fn on the stack in memory, and we're going to create new ones. And this one actually goes, this recursion depth is the depth of the linked list. It's like all the way down to the end is going to create, stack more and more things in the memory. And this is how it gets away with this time complexity. It's trading time complexity for space complexity. It's stacking all this stuff on the stack and then slowly unwinding it. And that uses a lot of space. And it uses stack space. For our small list, this isn't a problem. But if you start having a list that's like maybe 1 million long, you'll actually find this will break. This reverse application won't work because stack sizes in some operating systems are limited. 1 million may not actually be enough to reach it. This could get really, really high, and it's unlimited on some systems. There's no limited stack space. But still, it's not so nice. We want to limit the memory because when you do, CPUs don't like using lots and lots of memory like this, especially if you're going to redo it. It takes up space, it takes up a little bit of overhead. The stack itself isn't so costly. The way we'd have to fix this is we'd make a doubly linked list. You would have a previous node. I'm trying to think of, do we want to do a doubly linked list now? Or let's actually make a second one. Let's save this as double so that we can compare later. Double main. And this is a linked list. Now we have a double linked list. Let's say like main.leaf, but with a doubly linked list. And we'll change this now to be a, what if we just give it another name? Yeah, let's just give it another name. Double linked list. Double linked list, double linked list, double linked list. Double linked list. Okay. And I'll do this in a separate file for now. We'll show you how using parametrics you can make this easier after. But I don't want to take too long right now, so let's see what goes. So now we need a previous node in here as well. This is what defines a doubly linked list. Before I do that, let's do it this way. I said there's a way to reduce this because we're always talking optional shared node. We can do an alias of ref node first, and this is a shared node of type T. And or we might just want to say it's do we want to stick optional on it? What this would do is, I don't know if this is really that much, then we can say like ref node. That should work just fine. We're on double main. Invalid argument. Wow, what did I do wrong there? Let's take that out first. What did I change? Okay. This is a problem with copying and paste a large file. Suddenly I have an error, and I don't know where I did it. Okay, well, because we want to see that, the alias, let's go back to the previous one first. Now what did I do? It's really weird. This was working, and I don't even know what that error is anymore. Just remove double main. Oh yeah, leave main. Okay, that's just weird. There's something with the comments. Okay, I'm kind of lost as to what I screwed up now. And because this was working, and all I did was add comments. So let's just start commenting some things out and see where it fails. Not that. So it's something in there. Okay, so something to do with my list here, and I fear this might just be a small compiler bug. Line 3.8. Oops. Well, that's interesting. So let's comment everything out inside here. Sorry, this isn't meant to be this is going to happen as I work with the experimental compiler. So it's something inside here that we screwed up. Or I screwed up, not we. Where this is a common debugging technique I have when you have things like this. It doesn't come up in all situations where you're programming. When you work on tools like with preprocessors, compilers, and anything that processes a language, you often have these types of errors where you have to like hunt down. Okay, so we hunted something down, this one here now, which in these lines is causing the problem. I think it's the underscore. I think I screwed up something with the underscore. We didn't actually run it after that. That's weird. Wow. I'm surprised that underscore is causing an error in the compiler. I'm positive I have functions to do that. Alright, well let's just get rid of it for now. And I'll put a big to-do here. To-do. Didn't work with leading underscore in name. Okay. But let's do the aliasing bit first. To get back to what I was trying to do. If we wanted to reduce, we didn't want to share shared node every time, optional shared node. You might want to do an alias up node. Let's push first S node, and you could say shared node. Oh, I always get these characters wrong. And then you can say S node here instead. This should work the same. Now, this is if you really want to do this, and I'm actually not terribly upset with saying optional shared node each time, because it's very clear what I have, because there are cases where we don't have a shared node. There are cases where we deal with just a node. Some cases we have optional, some cases we don't have optional. So I'm not terribly unhappy with saying optional shared node each time. It's very explicit. I just wanted to show that if you do want to reduce this, if you have something you use like a terrible lot, and you could use an alias and simplify it quite a bit. But at the moment it's not too bad, so we'll just leave it that way. Okay, so now let's save this as a double main and try to do a double linked list out of this. Double linked list, we have to call it differently. Double linked list, double linked list, double linked list, double linked list, and double main does the exact same thing, which is correct. What we wanted to fix was the for-each reverse function to reduce its base complexity from n down to 1. We're going to do this by making every node link to the previous one. Here, previous is not a reserved word, so I could use previous. Remember, the reason we use next node is because next is a reserved word. Previous is not, but this would be really silly to have a naming convention where we have next node and just previous. So we'll say previous node as well. So we still have a head and a tail. We have to fix append first. Append, it's actually the only thing we have to fix, otherwise everything's correct. When we say head equals n, there's no previous nodes here. Still the first node has nothing special. It's when we attach a new node, going to say n dot previous node equals tail. So we say it points to the previous tail node, and then the next node points to n, and then tail equals n. And that's the only change we actually need for a doubly linked list. And this should still work. And I have a this makes sense now. I now have a memory loop in my structure, and Leaf will actually not clean this up automatically. And this is an error. You notice it actually ran up here. And this is an error that's this is part of the debug outputs. Normally you wouldn't actually detect this, but Leaf in debug mode from running now says, look, you have something that's, you know, there's still stuff in memory. And it's because I have this looped list here. And dealing with this in a lot of languages is a lot easier if you have automatic loop detection, but Leaf doesn't have that. And this is one of the reasons why things like linked list, you may want to just have forward pointing, because something like C++ also doesn't have that. Any standard things like C doesn't have that. I'm not actually sure Python has it, I think, some of the modes. Loop detection, I don't know, I think so. Java will have it, and C# has loop detection, but Leaf does not. Loop detection has a significant overhead depending on how you do it. But in any case, let's keep going with this. And to fix this problem, we can simply do a q.clear at the end. So let's write a clear function. And if we clear everything out, then the memory will be gone. And clearing is simply a matter of doing var n equals head. We start at head. And while we have n, we're going to say actually, how do we even do this? We have to assign a bunch of defaults. Yeah, let's just create a default one. Q is an optional. Say none. We need an empty one. The default itself doesn't have a way to reset, so we just create a none. So if it has n, then what we're going to do is we're going to say, alright, how do we do this now? If we have to clear the next one and the previous one, we can certainly say get opt n dot previous node equals none. We for sure don't have that. Then n equals get opt n dot next node. And this will clear all the previous nodes, but we have to clear next node somehow. So we need to have a temporary here, var nn. That's probably a really bad name. So let's call this current. Well, it has current, next. And then we say current node dot next node equals none. This clears all the links. And then current equals next, and head equals none. And we clear it up, and that should get rid of our error. So that gets rid of the error because I forcibly cleared up the list. This is what you have to do in languages that don't have loop detection. You have to manually clear up any memory loops. And we created this memory loop by having the previous node pointer. And this will also just clean it up. And this just goes through the entire list and breaks up all the links and gets rid of them. And that, again, makes our memory go back down to 0. And it also empties out the list. We actually cleared the list. Now if you did a dump q at the end, we're going to have nothing output. So we have an empty line because there's nothing in it. So clear is a function we need anyways. So it's not so bad to write clear. Clear could be a little... If you have a memory, if you have a program or a language that does automatic loop cleanup, you can just remove this part and just say head equals none, and that will be enough to clear the list. But I don't have that right now. I'm debating adding it to link or to Leaf. It's a bit complicated, and I have to debate when to do that. Okay, but now we have previous node. We did the append adds it, and the goal here was that for each reverse should be a lot simpler now. For each reverse should look pretty much identical to for each. So let's drop all that code. And now we do for n equals tail. We start at the tail, and while we have a value, we're going to get the value n. And then n is going to be, it's going to be just like for each, except we're going backwards now. Previous node. And it does the same thing. That's perfect. So what we've done is we significantly reduced the complexity of for each reverse by adding a previous node pointer. What this does, it reduces the space complexity down to 1. We no longer have the recursion. We no longer have these items being added to the stack. This is a trade-off you make. So by adding a second pointer and increasing the complexity of the data structure, we were able to simplify the complexity of this for each reverse function. Now notice, however, none of these functions, dump and dump reverse and sum, they don't actually change at all. And this is one of the things about dealing with data structures and abstract names. They just didn't change. They didn't care that we have a double thing. The code changed the same. Now if I did my parametrics correctly, what that really means is that for dump, it doesn't care what it takes, as long as it has a for each. Dump reverse, it doesn't care what type it takes. As long as it has a for each reverse, it works. Same with sum, it doesn't care. It still returns an integer all the time. It's a little bit more restricted. It says it doesn't care. As long as for each exists and the items have a value, it works. This is one of the value of parametrics, is now we have code that doesn't care what type it is. So now what I'm going to do because of this, I'm going to copy this back into the other main file again. Or actually, let's start doing this differently. Let's start splitting up these files. We're going to take this linked list and put it in its own file. Double linked list, LAF. Keeps reducing the size. Okay, and then open up main. And we have linked list. Put that in its own file. Linked list.leaf. And I have to clean up. I want to get rid of double main.leaf because, oh no, we need to get the files at first. Yeah, no, we can get rid of that. Double main.leaf. And I gotta get rid of my old main.leaf. This is one I was working on before. And get rid of whatever swap file Kate decided to create. Now we have 3 files. I'm going to go into main. And you keep increasing the font size because it keeps resetting it because it's just temporary. And so main is still using a linked list. I'll reduce font size 1 so it's linked. So now we'll leave star.leaf. This is just saying use all the files now. We're previously saying main.leaf. I'm saying star because all the files in this directory are now part of this program. It's supposed to take a directory too, but I don't know if I ever took dot. It does work. Great, perfect. So leaf dot, run the project in this directory. It just uses all the files. And that lets us split it up. And you notice in leaf, we don't have to specify the order to these files. It doesn't matter where this import is, where these dumps are, who cares? There's no ordering to any of it. You can put the main function where, indeed, we can put this main function at the top because it makes more sense, and put the dump functions further down, and it's going to do the same thing. It works exactly the same way. It figures out the dependencies. But now we said, this is what we said, this queue doesn't matter. Dump works regardless of what list we have. As does sum. These are parametric functions, meaning they take any type they want. And that's what we said, because, and then we can simply switch this with a double linked list. I forgot to clear it. Okay. What we're going to have to add is a clear to the singly linked list case, because there's no field known as clear. So we open up the linked list. And we have to add a clear here. Define clear. Now this is where it gets really interesting, because there's no loop. Clearing is really just as simple as it is in the doubly linked. In the case where I said you have a loop detection, we really just need to create an empty value, and we can create that directly inline. Optional shared node t, because the default of a value is optionally not set. Then tail equals head, because they're both not set, and that will work now. Oops, I thought it'd work. Let's just check something. If that doesn't work, it means I have another compiler bug, but that's okay. That's why I'm doing these things as well, so we find these bugs in the compiler. If you're interested in working the compiler, just let me know. There's always lots of work to be done. And this is type optional. .33. Alright, so this is another to-do. Should have worked. And it's these little things like this. The language is very complex, and although everything's supposed to be orthogonal, sometimes you have weird little rules, little constructs that just didn't quite work as expected. And this works in most cases, but these specific types, and this is why I like doing all these things, these examples, because we can really look at finding these corner cases and working them out in the language. Okay, but the clear here is simpler. And so what I was showing is that in main, doesn't matter whether you have a linked list or a double linked list, this rest of the code in main, all of this doesn't change. Because Q has the same interface, the code works exactly the same. And we can actually make this more interesting. We can do var, let's say run test, and it takes the Q instead, and it's not going to care about Q, and we'll do this all in there. Q, and append run test Q. Okay, where did I put it here? Yeah. It might be because the return value. Uh-oh. Well, there was a theory. This should have worked. Maybe it doesn't. 8:15. It's right here it's having a problem resolving what it should be. And I'm not clear why. Alright, well, I'll just backtrack out of that. I'll mark that on my list of things that should have worked as well. But at least you can see the effect right here. Double linked list works. But now it's going to be the same error at line 22. Oh, because I still have run test and get rid of it. And linked list. And it's because they both have the same structure. So we have the forward linked list and the double linked list. And let's just go over the double linked list again, just to explain it a bit. So the double linked list, increase the size again. It has the same space complexity as the singly linked list. Now you may be wondering why does it have the same space complexity? It uses more space. It has a previous and another pointer. And that's absolutely correct. This actually takes up more space than the singly linked list. However, when we're measuring complexity, we don't measure actual amount of memory. We tend to measure the class of memory. And what this is saying is that the amount of memory extends depends on the number of items in it. Sure, this has 3 values, so it's 3 times n, but when we're comparing algorithms, 3 times n, 2 times n, we're just looking at the classes of these things. What order of magnitude, because we want to know, is it n squared instead, is it n log n? This is the important part at this point. When you're doing, in practical terms, you might very well make the difference. Maybe you don't have the memory to say previous node. Maybe you're on an embedded machine where every bit of memory still counts, and you know, you could be doing your small Arduino project and you say, look, I don't have much memory. This little chip has no memory on it. I don't need to do reverse I don't need to do reverse, or if I do reverse, I can afford to do the stack reversal. So you have to make these options, but the complexity says, look, it just related to the number of items in it, and that's what n's saying. Theta of n saying the memory is directly related to, or proportionally related to, the number of items in it. Okay, and so we have our head. Head is the first item in the list. It's an optional because we may not have an idle. It's shared because we don't want to be by value. And it's a node of type T. Again, type T can be anything. Maybe we should show that. Let's actually show that this can be type anything. Let's create a second test here. Var R. Make a linked list of type character. And q.append A, q.append B, and then dump q. Where am sorry. R. So now we have the list AB. And that's so it works with other types as well. To make it even more fun, let's just put some character in there. What Unicode character do we want? Is there a leaf in Unicode? Fallen leaf. Maple leaf. That sounds better than fallen leaf. Okay, my font can't show it, which may be an issue. Neither can my console, so that's not so much fun if I can't see it. My browser Arial times... Well, that's really weird, actually. I should be able to see it. If this is part of the standard character sets, and it shows in my browser... What about fallen leaf? Does fallen leaf appear? No, I don't have fallen leaf in this font either. We're going to have to do something boring. Typical emoji. Well, let's do Unicode sad face then, because we don't have our little leaf. We wanted a leaf, but we don't have it. These pages. This we should have without the spaces. Yeah, it's really hard to see in my console. It's okay, it's this frowny face. But there, because we didn't have a leaf, we'll put the little frowny face. And in Leaf, this is a character. Leaf's characters are 32-bit characters. It's the full Unicode set of code points, so they directly map to a code point. And I'll get into that in the future one. But our linked list can now show these things. We actually have... This should show we can store anything in the linked list, including little smileys. And obviously the sum function won't work. You notice the sum takes integer, so now if we try to call sum on this, rc equals sum r, it'll complain. In typical Leaf format where I don't have error handling yet, it's a mismatch in fundamental. And this is one of the cases where, yeah, parametrics can go a little bit weird, because it's way down here. Now from this trace, you don't actually know that it's from this sum function here. So this is something I have to work on. This is why error handling is not simple, because it's not the sum function that's wrong, it's the caller that's wrong. And C++ actually has this exact same problem when dealing with parametrics, is that because it doesn't know at the point where you're calling that there's anything wrong, and at the individual function, there's nothing generic it can tell you that's wrong. You get weird error messages somewhere deep in the stack saying, look, these types don't line up, and you get confused. And this was the proposal in C++ for concepts. Concepts would have fixed that. I think that was the intent, is that you would be able to say, write in this function here what you expect. And so you'd be able to say something like collection of integer. And this is something I actually do want to add to the Leaf, that we will be able to say this is a collection of integer, but we don't have anything that expresses this yet. So we have to leave it open with the unhappy error message, and we just won't take the sum of it. It's not terrible. This is, in a dynamic language like Python, you'll get these same errors where you call something with the wrong type and then you'll get some wacky error. You have the exact same problem, you don't know where it is. But fixing this is something I'd really like to do because it is a common error. And using characters. So we use characters, and here we have integers. There's only so much more we can add to the list. Let's show one where sum does work. That's not just integers. Let's change the sum to return floating point, which means I'm going to have to explicitly mark it because the default is integer. And okay, it's on the same line now because now it's trying to add an integer to a floating point. So we're actually going to say lossy, and this is going to sound really weird. Now, why do I do lossy? Because an integer is the natural word size of my target machine, which is 64-bit. A floating point, double precision, is also 64-bit. And the problem is that a 64-bit integer cannot be represented fully in a floating point when it gets the higher number of integers. And this is why Leaf was complaining here, because it doesn't want to convert it. It has no way to convert the two values, and the error message should be improved saying, look, it would lose precision, and Leaf does not allow anything that would allow data loss at first. So we're going to say lossy on the assumption that we can actually store it, and this is something we have to be aware of now. But the reason I wanted to do this is to show that this also works with float, using float, var f, linked list, float, r to the pen 2.5, r to the pen 7.1, r to the pen 3.7. We dump r, and we can do standard print line sum f of the float, sum float, sum of f. F, made a mistake. Okay. So now it works for floating point as well. Even the sum function, the sum adds up correctly. I hope that's adding up correctly. 10.8, 12.8, 13.3. So that's adding up correctly. And the double linked list should work the same as well. Double linked list on any of these. Because we forgot to call clear again. Yeah. Okay, so that works fine, either one. And I think that covers about all I wanted to do today. It may have been a bit much, but you can keep tuning into my series. We'll learn a bit more about Leaf and algorithms. If you have questions about this algorithm, feel free to just ask me on Twitter or go to my blog, or I'll also post this to the Google group as well. So if you go to leaflang.org, you can get to the Google group, and I'll post this here about what we did, and you can ask questions there as well. Feel free to ask questions before I get there. And okay, and actually, what am I? There it is. And that's what I would say. So if you have questions, please ask. And next time I'll think of another algorithm to do. And if there's anything you'd like covered, just let me know. If you want me to keep looking at this again, if you have questions about it, I don't mind doing another episode about it. The series is meant for not just learning Leaf, but actually learning about algorithms and general things about algorithms. I'm using Leaf just because it is my language and I need to work on it. And we find simple errors with this, and it also exposes you to new concepts. And that's all I have for today. I'll put this on GitHub, this code, and I'll post it to Google News, or the Google Groups, sorry. And thank you for watching, and until next time.